Pluto is a far-off and puzzling planet that was once a member of our nearby solar system's planetary family. However, recent alarming declarations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a stunning disclosure. They suggest that this icy world is on a potential crash course with Neptune. But how might this occur, and what could be the outcomes of such a huge event? Are we witnessing an intriguing cosmic peculiarity, or is there something more to this approaching celestial collision? Join us as we explore the possible outcomes of a Pluto-Neptune impact. Pluto, a former planet that was downgraded to a dwarf planet partly because of its unique orbit, remains a subject of interest and study in the galactic community. According to recent predictions by leading researchers, Pluto's trajectory is dangerously close to Neptune's. Both Neil deGrasse Tyson and Michio Kaku are raising the alarm about a potential impact between these two planets that could pose a significant danger to Earth. How is such an event even conceivable? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It takes an astonishing 248 years to complete a single orbit, meaning that since its discovery in 1930, it hasn't even completed one full revolution. However, the intrigue doesn't stop there. Pluto's orbit is marked by its exceptionally curved shape, deviating significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more curious is its inclination, calculated at 17 degrees to the ecliptic plane. The path Pluto follows is much steeper compared to those of the other planets. This inclination and eccentric nature add layers of complexity to its orbital pattern. Quite possibly one of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's path. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This prompts the natural inquiry: why hasn't Pluto slammed into Neptune? The answer lies in the gravitational influences of other planets. The investigation of Pluto's orbit began shortly after its discovery. Initially, astronomers attempted to figure out its unusual trajectory. Unlike other planets whose orbits lie somewhat close to the ecliptic plane, Pluto's path stood out with its steep inclination and eccentric shape. The mystery deepened with the realization that Pluto's orbit indeed crosses Neptune's. The strength of Pluto's orbit amidst these complexities is evidence of the intricacies of space mechanics. The three-body problem in space is about figuring out how three objects like Pluto, Neptune, and the Sun move and influence each other with their gravity. It's akin to trying to predict where they will go based on where they start and how they pull on one another. In Pluto's case, this problem illustrates how its orbit, Neptune's path, and the Sun's gravity all work together in a complex manner. The terms alpha libration and scope libration, along with the VZK oscillation, are part of this riddle. According to astrophysicists, what's keeping all planets in their orbits is a phenomenon called alpha libration. With regard to Pluto and Neptune, this term means that when Pluto crosses Neptune's orbit, it is positioned about 90 degrees away from Neptune. This spatial separation is significant in keeping their paths from colliding. Scope libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it's positioned significantly above their orbital plane, providing an extra layer of protection from potential collisions. Another important factor in this scenario is the VZK oscillation, named after three researchers, Bond, Zippel, and Kai, who studied how objects move in space. It pertains to how three celestial objects, like Pluto, Neptune, and the Sun, pull on one another with their gravity. This pulling influences how they move. In Pluto's case, the VZK oscillation helps us understand why its path around the Sun is so unusual. Despite Pluto's orbit appearing chaotic, this oscillation aids in maintaining a smooth trajectory. All these factors help keep Pluto's orbit stable, ensuring it doesn't collide with Neptune or lose its course. This three-body problem aids in understanding how these paths change based on how celestial objects pull on one another. Focusing on this helps us learn about Pluto, our solar system, and distant worlds and their stars. Mathematical simulations in the late 1980s revealed that despite these stable properties, Pluto's orbit is actually tumultuous, with minor deviations in initial conditions leading to significant differences over millions of years. However, these peculiar properties of Pluto's orbit have been found to maintain stability over exceptionally long timescales, effectively keeping chaos in check. Recent computer tests have helped us understand how the giant planets, like Neptune, Jupiter, and Saturn, influence Pluto's path around the Sun. Neptune has a special relationship with Pluto, where for every 2 orbits Pluto makes around the Sun, Neptune makes 3. This connection helps keep Pluto's orbit stable. However, Neptune isn't the only one to pay attention. Jupiter's gravity also plays a major role in safeguarding Pluto's orbit, and Saturn contributes significantly as well. These tests show that Jupiter's gravity alone is powerful enough to ensure Pluto remains on a stable path for an extensive period, even billions of years. It seems that Neptune, Jupiter, and Saturn are working together to ensure Pluto continues to move safely in space without running into trouble. These phenomena are fundamental for maintaining the order and consistency of celestial bodies' movements in the universe. Without these components, the solar system, as we know it, would be a place of much greater chaos and unpredictability. Bodies like Pluto could potentially collide with others or be ejected from their stable paths, leading to a domino effect on other celestial bodies. For Pluto, especially with discussions about a potential collision with Neptune in the future, understanding its orbit is truly significant. This gives us a clearer picture of the solar system's dynamic nature. The case of Pluto illustrates how even the most seemingly unstable orbits can achieve a state of harmony through the complex interplay of gravitational forces and orbital mechanics. It also highlights the importance of continuous observation and investigation of these phenomena to better understand our place in the universe. Exploring the depths of space often leads us to confront the strange nature of celestial bodies, and Pluto's orbit is a perfect representation of this strangeness. The concept of orbital chaos, which refers to the delicate dependence of a celestial body's path on its initial conditions, is strikingly demonstrated in the case of Pluto. This means that even slight variations in the dwarf planet's position or speed can fundamentally shift its long-term trajectory. In the vast expanse of our solar system, Pluto occupies a unique position that challenges our understanding of planetary classification and dynamics. Since its discovery in 1930, Pluto has undergone extensive study, leading to significant discoveries about its composition and behavior. One of the most captivating features of Pluto is its surface, which is an intricate tapestry of ice, rock, and various compounds. The New Horizons mission, which flew by Pluto in July 2015, provided remarkable data about this distant world. The surface of Pluto is characterized by vast plains, towering mountains, and deep valleys. One of the most outstanding features is the Sputnik Planum, an immense heart-shaped plain that is primarily made up of nitrogen ice. This region showcases a diverse array of landforms, including large ice shelves and what appear to be flowing glaciers. The presence of these features suggests that Pluto may still be geologically active despite its great distance from the Sun and low temperatures. Another intriguing aspect of Pluto is its atmosphere, primarily composed of nitrogen, with traces of methane and carbon monoxide. Pluto's atmosphere is thin, yet it exhibits fascinating seasonal variations. As Pluto approaches the Sun in its elongated orbit, its atmosphere can expand and contract. This dynamic behavior reflects the complex relationship between Pluto and its environment. During its closest approach to the Sun, some of the atmospheric gases may freeze out onto the surface, while as it moves farther away, these gases can sublimate back into the atmosphere. The interaction between Pluto and its largest moon, Charon, also adds complexity to the system. Charon is relatively large compared to Pluto, with a diameter about half that of Pluto itself. This size ratio means that both bodies are in a mutual orbit around a point in space that lies between them, rather than Pluto simply rotating around Charon. This unique relationship contributes to the intricate gravitational dynamics in the region, affecting the orbits of other objects in the Kuiper Belt. The Kuiper Belt, a region beyond Neptune populated with small icy bodies, is home to numerous other dwarf planets and potential impactors. This belt is a reservoir of ancient material from the early solar system, providing researchers with a glimpse into its formation. Pluto's orbital characteristics may offer insights into the movement patterns of these distant objects, suggesting that interactions with larger planets may have played a significant role in shaping their current orbits. One of the key implications of understanding Pluto's orbital elements is the potential impact on our appreciation of the solar system's evolution. The gravitational influences from neighboring giant planets like Jupiter and Neptune can alter the trajectories of smaller bodies, including those in the Kuiper Belt. Such interactions can result in shifts in orbits, potentially leading to collisions or ejections from the solar system. As scientists continue to investigate the details of these interactions, they may uncover broader patterns that govern the behavior of celestial bodies throughout the cosmos. The study of Pluto also raises philosophical questions about classification in astronomy. The decision to rename Pluto as a dwarf planet in 2006 was controversial, igniting discussions about what constitutes a planet. The International Astronomical Union's definition focused on criteria such as orbital dominance and size, leaving many to ponder the implications of such classifications. This ongoing discourse reflects our evolving understanding of the universe and underscores the need for a flexible approach to categorizing celestial bodies. Furthermore, the potential for future exploration of Pluto and the Kuiper Belt remains an exciting frontier. With advances in technology and mission planning, researchers envision sending additional spacecraft to study not only Pluto but also other distant objects that share its orbital characteristics. Such missions could provide invaluable information about the primordial materials that shaped our solar system, potentially offering clues to the origins of life on Earth. The study of exoplanets, planets beyond our solar system, is another captivating area of research that intersects with our understanding of Pluto. As astronomers discover an increasing number of exoplanets, particularly in the habitable zones of their stars, the lessons learned from studying our own solar system can inform theories about planetary formation and habitability. The conditions that allow for stable orbits, atmospheric retention, and geological activity could shed light on the potential for life elsewhere in the universe. Finally, public interest in Pluto has persisted, fueled by its complex status and the stunning images returned by the New Horizons mission. The dwarf planet has captured the imagination of people around the world, sparking a renewed appreciation for the vastness of space and our place within it. As we continue to unravel the mysteries of Pluto and the celestial bodies that inhabit its corner of the cosmos, we are reminded of the profound wonders that the universe has to offer. Do Pluto's unique qualities extend beyond its physical properties and orbit? It also serves as a crucial case study for understanding planetary dynamics and the behavior of celestial bodies. The evolution of Pluto is believed to have occurred in the early solar system alongside other Kuiper Belt objects. Studying its composition can shed light on the conditions prevailing during the solar system's infancy, potentially illuminating theories about the formation of terrestrial planets, including Earth. Recent research suggests that Pluto may have a subsurface ocean, a finding that could transform our understanding of its geology and potential for harboring life. Data from the New Horizons mission indicated that some regions of Pluto's surface, such as the icy mountains, might be composed of water ice, which behaves differently from common rocks under low temperatures. This discovery invites further investigation into the possibility of liquid water existing beneath its icy crust, raising intriguing questions about the potential for life, even in such extreme conditions. Moreover, Pluto's interaction with its environment can provide insights into atmospheric science. The seasonal changes in its thin atmosphere offer a natural laboratory for studying atmospheric dynamics on a planetary scale. Researchers are particularly interested in how the interplay between solar radiation and the surface can lead to complex weather patterns similar to those observed on larger planets. The significance of ongoing observation of Pluto and other similar celestial bodies could not be more critical. As more missions are planned, particularly those targeting the outer reaches of the Kuiper Belt, we expect an abundance of new data that challenges existing theories and expands our understanding of planetary science. Each discovery adds another piece to the puzzle of our solar system's history and the processes that govern its evolution. Through these investigations, Pluto remains a symbol of the relentless quest for knowledge about our universe, inviting both scientists and enthusiasts alike to ponder the mysteries that lie beyond our earthly domain. Pluto continues to inspire a wealth of research across various scientific disciplines. As astronomers refine their techniques and technologies, the possibility of uncovering more about this enigmatic dwarf planet becomes increasingly tangible. Future missions might not only revisit Pluto but also explore other Kuiper Belt objects, enhancing our understanding of the early solar system's evolution. Moreover, the study of Pluto plays a critical role in enhancing our grasp of celestial mechanics. Analyzing its interactions with nearby bodies offers insights into the gravitational influences that shape orbits over time. Understanding these dynamics is crucial, especially as we investigate the potential for similar processes occurring around exoplanets. Astrobiologists are particularly interested in how Pluto's unique conditions might parallel those found on other icy bodies, such as Europa and Enceladus, which harbor subsurface oceans. Investigating these environments could yield significant findings regarding the ingredients necessary for life. Additionally, public interest in space exploration has surged, largely due to Pluto's captivating imagery and the dramatic narrative surrounding its reclassification. This fascination fosters a greater appreciation for astronomy and planetary science, motivating educational initiatives aimed at inspiring the next generation of scientists. As we continue to study Pluto, its complex nature will likely yield profound revelations that expand our understanding of the universe.